Kent is very sorry that he couldn't be here to talk to you all today. He asked me if I would stand in his place, and I will do the best I can. If you view this presentation at the end, you say, what the heck is that guy talking about? That reflects on me, that does not reflect on Kent. But look, y'all, I was talking to some folks yesterday evening, and it was brought to my attention that maybe some folks think I have a little bit of an accent. And that concerned me. I said, Mela, if they can't understand me, then we're not going to communicate. So I decided to ask my wife. I said, do I have a funny accent? She said, well, you don't sound any funnier than usual. Well, I like to point out my wife is from up by Shreveport, up north of I-10, and they all talk funny up there. So I called my partner, Chris, from high school. I said, hey, Ba, you know, he lives over by Brobridge, and they all talk funny over by Brobridge. And I said, do I talk funny? And he said, no, man, you sound fine to me. So I surveyed all the experts I know, and they told me I don't talk funny. So I would like to point out, though, I do sometimes look funny. And this photo shows you why I never make a bet on college football anymore. Because I had a bet about the LSU-Wisconsin game, and now I had to wear that ridiculous hat me. So, all right. So what I'm going to talk about this morning is I'm going to talk about some work that's been going on related to feed efficiency and feed intake in dairy cows. And I've outlined 3 of the key points I'm going to talk about here. What is it? What are we going to do with it? How are we going to take this information and use it in genomic prediction? And then I'll talk a little bit about how we might put it into a selection index. Now, what is feed efficiency in dairy cattle? Why do we talk about feed efficiency? We already know that feed accounts for at least half the cost of production of a unit of milk, whether it's a pound, a kilogram, whatever, it doesn't matter. So what we're interested in is we're interested in cows that take in as little input as possible and give us as much output as possible, right? Those are more profitable cows. So we're interested in outputs like milk and meat, things that you all are paid for. There are other outputs from the cow, manure and things like that, that most folks don't get paid for, so we don't consider that in our calculations. And then we worry about the inputs, you know, the feed we have to put in, the energy, protein, and nutrients that go into the cow. And then there are related knock-on costs. So if you have to fertilize your field, you have to buy seed, you have to depreciate equipment, all of those things. And then we also, at least as geneticists, we worry about biological efficiency versus economic efficiency. There can be a difference in efficiency between 2 cows, but if that difference is very small, it may have no practical impact. And you could argue that that's maybe a philosophical distinction, but we do talk about it. And then there's the question of variation at the cow level and variation at the herd level. So if there's very little variation at the cow level, that means that we have to turn to the herd level and say, can you change your management practices and that sort of thing to improve the efficiency of your animals? I'm not a nutritionist. I can't draw all 20 amino acids. My understanding from the nutritionists is that we're not concerned only about the efficiency of energy utilization, but we're concerned about the utilization of things like protein in the diet. However, protein is rarely the limiting factor in the diet when you're talking about production. It's typically energy. So we're focusing here on how efficiently a mid-lactation cow uses the energy in her diet. Why do we focus on mid-lactation? Because typically by that point the cow is past the stage of negative energy balance, and she is again capable of consuming more nutrients than she needs, so she's not metabolizing body fat and things. And why does it seem like we've been talking about this so much in the last few years? Well, the answer would be genomics, and so let's talk about why. The cost of measuring feed intake hasn't really changed on a per cow basis. What's really changed is the cost of collecting enough information on individual bulls to do evaluations. So we can see in the old days, in the pre-genomics days, if we had 1,500 young bulls a year and we wanted to collect about 100 observations per bull, it would cost us, we'd have to phenotype 150,000 cows a year at an annual cost of about $75 million. That's clearly prohibitive. With genomics, the measurement cost of the cow stays the same, but now we genotype the cow at $40, we develop a reference population, and then we can genotype many times more young bulls with a one-time cost of about $13 million and then just a modest cost ongoing annually for genotyping and data collection. So genomics has changed the economic feasibility of using feed intake data. And I'm going to talk very briefly about why is it still relatively expensive to measure, why is it difficult to measure. These aren't dairy cows, not even in Brazil. But this shows an example of the equipment we use to collect these measurements. So these are gross safe feeding cells. We have 32 of them, for example, in our research dairy in Beltsville. So each of those tubs is on a set of scales, basically. There's an RFID unit built into it, so when the cow starts to eat, it measures the weight at the beginning of the feeding period, and then it reports the weight when she leaves the trough. So we have by difference, we know how much by weight she consumed. These systems are fairly expensive to install, and they require a lot of maintenance. They sometimes get fidgety. I know many of you have had experience in your own barns that these wireless systems don't always work particularly well when you've got structural steel and things like that. This is still better than 10 years ago. 10 years ago, what you would do to measure feed intake is, at least if you're a scientist, is you send your graduate students out and they feed the cows. And you know how much feed you put out in the front. When the cow's done, you sweep it all up and you weigh it. It's very time consuming. There's lots of room for measurement error. So these electronic systems work much better. And then I believe Jeff talked yesterday about a new system that actually takes some volumetric measurements with cameras to look before and after and figure out how much the cow ate. Now, I was excited about this at first because I said, hey, I can install that in our barn at the dairy and we can collect feed intakes for all of the cows, not just for 32 at a time. But then I realized something. I realized the price is going to magically be about $10 less than it would cost me to install a GrowSafe system. So we'll have to see what happens there. So when we really talk about using feed intake in genetic improvement programs, we're interested in a measurement that we call residual feed intake. So we're not actually proposing to do selection on dry matter intake. So what is this residual feed intake? Well, we record the actual dry matter intake, so how much feed did the cow actually eat? And then we use some NRC equations to figure out, at least in theory, how much was she expected to eat. So what you see above the line here, we've plotted the observed versus the predicted. And all the dots do is they differentiate between first lactation cows and later lactation cows. And so there's one observation per dot, so that's an observation on a cow. Animals below the line eat less feed than expected for their size and body weight and level of production. So those are the animals that we're most interested in because they eat less and they do more with it. The animals above the line eat more than we expect and they do less with it. So when we talk about selecting for residual feed intake, we're trying to find animals that are more efficient in terms of how they utilize the energy in their diet. So, as I said, I'm not a nutritionist, but I thought this was fascinating, and I'm sorry I didn't realize that red was going to be so hard to read. But I thought these nutritionists were on top of things because they know pathways, they know biochemical mechanisms, they can tell you the only enzyme-bound membrane, the only membrane-bound enzyme in the Krebs cycle. So I thought they really knew how all this stuff gets partitioned out. But that red triangle in the pie chart says unknown. So there's a fair chunk of things that they don't yet understand either about how the cow metabolizes nutrients and uses them in her body. So that gave me a little hope because I think if I drew a pie chart, I'd say there's even more than 27% of things I don't know. And on the left, we're just seeing a reminder of how we calculate residual feed intake. We take everything the cow ate. Then we subtract off the energy that went to things like manure, urine, methane, other gases the cow emits, and that gives us a measurement of her net energy intake. So once we take away maintenance, we take away the maintenance from the net energy, and then that tells us what's left over is the energy that was used for production and for, say, growth, that sort of thing. So, one of the questions that we've been trying to understand over the last several years is when is the best time to measure residual feed intake? Because none of the research organizations, none of the universities, not Dairy Forage and Madison, not our group, we can't measure all of our cows all of the time. We don't have the equipment to do that because of the expense. So we tend to do trials where we measure the intake of individual cows for 60 or 80 or 90 days. So this is the result from some recent research we did in Beltsville. Dr. Aaron Connor did it. And what we found is that the best time to measure is a window that's centered here at about 180 days in lactation. So as I mentioned earlier, that's past the period of negative energy balance. Hopefully she might be putting a little bit condition back on. And what the curve is it's a regression on the correlation. Each dot is the correlation of feed intake measured on that day with the total lactation feed intake for that animal. So these data are from cows that we've tracked in Beltsville, and we've measured their feed consumption every day of the lactation so that we were able to answer this question. And you might think that this is an academic question. What do I care when in the lactation you sample and for how many days you sample? Well, the issue is that we're trying to collect as many phenotypes as possible. Given that we're limited in the equipment that's available, we want to use the equipment for as short a period of time per observation as we can so that we can collect information on more cows. This is maybe a little bit different way to represent those data. It's just saying, about mid-lactation. Obviously, the longer your sampling period, the higher your correlation is going to be. But if you can go for 60 or 80 days, you're going to do pretty well. So then how do we actually implement genomic selection for feed intake? Well, we build a reference population. We estimate our SNP effects, right? This is probably review for everyone. We genotype some calves, and then we make selection decisions. It's the same conceptually as it is for any other trait. Now, to collect enough information, enough observations to do this for feed intake, Mike Vandehar at Michigan State assembled a consortium of several different institutions, and then they received some funding from AFRI, right, USDA's competitive grants agency. And you can see it was several land-grant universities. So, Michigan State, Iowa State, University of Florida, Dairy Forage, we were involved, Virginia Tech, the minor institutes, so a couple of private, Purina was involved. And through all of that, we were able to collect a little over 4,000 observations on a little over 3,800 cows. And, I was mentioning that the limiting resource is the equipment available to measure the intake. So it took all of these institutions a period of several years to get to a little over 4,000 observations. And that's going to be important later on. So we've got these approximately 4,000 cows, 4,800 observations, and the phenotype is residual feed intake. So all of the data collected as part of this study from the different participants gets sent to Michigan State University, where all of the data are processed the same way. They're adjusted for body weight change and milk energy and all of these things the same way. Most of the trials were 42-day trials in mid-lactation. And then my postdoc imputed all of the genotypes up to the high-density chip because we wanted to ask some questions about the genome that I'll get to later. And my colleague Paul Van Raden last year said, okay, we're going to take all of these data and we're going to see if it's feasible to calculate genomic evaluations for the whole US population. And I think most of you probably know by now that if Paul sets his mind to something, he's going to do it. So we set up a genetic evaluation model that includes the typical things that you see in milk and everything else. So we've got the animal's genetic effect, the permanent environment herd by sire, we've got management group effects, but Paul also put in genetic regressions on body weight change and on milk energy. The reason he did that is because RFI is phenotypically uncorrelated with production level and the size of the animal, but there was still a remaining genetic correlation. So that meant if you selected on the phenotype, you might see some unexpected changes. So he actually performed an evaluation on genetic RFI, which is a slightly different, but the results are similar. So we used the genomics to calculate evaluations for 1.4 million genotyped Holsteins, and then we also got evaluations for all the 60 million Holsteins that are not genotyped through the animal model. So the cows that have direct records, they have the highest reliability. So if you see average, theoretical, and observed reliability. So in theory, given the number of records we had and the heritability, for example, for the cows with direct data, we would expect a reliability of 31%. What we actually observed was a reliability of 26%. You can see that for the heifers, it's a little bit lower, and for the bulls, it's lower still. It's lower for the bulls because most bulls don't have daughters that have direct observations of residual feed intake. So what this tells us is that it's technically feasible to calculate these genomic evaluations, but the reliability is going to be much lower than we expect for other traits. And so as a reminder, what a low reliability means is there's a lot of uncertainty around our prediction of the breeding value. So if we say an animal's residual feed intake is plus 0.5, but the reliability is low, the animal's true feed intake could be, minus 1.1, or the true value could be plus 1.1. So lower reliabilities mean more uncertainty, and that means more risk. And so that gets to be a question for groups like your Genetic Advancement Committee, Dairy Sire Evaluation Committee, and the Genetic Evaluation Methods Committee that's advisory to Council on Dairy Cattle Breeding. The question gets to be, is the trait valuable enough that we're willing to accept this level of uncertainty about the results? So in better trying to understand how these RFI evaluations were working, Paul decided to study somatic cell score. The reason he did this is because somatic cell score has a similar heritability and has a fairly similar repeatability. It also has a low genetic correlation, low phenotypic and genetic correlations with yield. So no, his argument is not that somatic cell score is the same thing as feed intake. It's that it has similar statistical properties. So we can ask questions about the reliability if we use correlated traits and things. Okay, and what we have now is when we look at the top 100 progeny tested bulls, we see that they have lots of milk daughters, which produces high reliabilities, but on average, they average about less than 1/10 of a daughter each for RFI. So this is very, very little information, and it's not going to help very much. It's actually worse for the top 100 young bulls. Now, I want to emphasize, I'm not criticizing in any way the breeders of these animals. It's not their fault that the daughters haven't been phenotyped. It's simply trying to help folks understand the amount of information available for RFI is much, much lower than for other traits, even things like the health traits that we have evaluations for now from CDCB. And so we see relatively low expected genomic reliabilities, below 20%, so we're down there not much better than parent average. And then what Paul also found is that the correlation of records in the research herds with records in the overall population was a little bit lower too, so he had to do some weighting. And once you do all of this weighting, you actually find that the observed reliability of somatic cell score once it's weighted is 11%, and so he adjusted the RFI reliabilities to have a similar degree of correlation. But, okay, I'll get to that. So the reason we have a higher reliability for other traits than RFI is we have more observations. I think that's what I've been talking about. That's pretty obvious. It's good for young bulls, it's good for proven bulls. But you look at RFI, and even the proven bulls have pretty low reliabilities. But the issue is that potentially, even with low reliability, and even with few phenotype daughters, the overall value to the industry of improved genetic selection for feed intake could be substantial. So some very conservative calculations from Paul are $4.5 million a year. It could potentially be greater than that, depending on what the market does. And the way Paul got to those numbers is we put some values on average, like average feed intake, average production. Then we valued dry matter intake and the marginal value of another pound of milk. These are pricing data collected from various sources, Economic Research Service and others. Then converted it to a lifetime basis at 2.8 lactations, and came up with 16% of the emphasis in new net merit would potentially be placed on residual feed intake. So this is showing you the breakdown, and I want to appreciate what was said by Dr. Roll, because if you look in the bottom right, you see milk yield, and you see -1 in front of it. That means that we have a very small but negative weight on milk production in net merit. But if I talk to anybody who's not a dairy cattle geneticist, and I include dairy cattle nutritionists and reproduction folks and all, everybody thinks our selection objective is milk. We've done an absolutely terrible job of communicating, even with people in our industry, what it is we're trying to change in the cow. So I'm glad I'm not the only person who's observed that. I was worried that it might just be me. So we put much more emphasis, for example, on fat and protein yield than we put on milk. But if we put residual feed intake into net merit, we'd be looking at something like 16% of the overall emphasis because of the cost of feed. Now, how is this different from the feed efficiency component that's in TPI? So I went back and looked at it to refresh my memory, and there's an indirect predictor. I say indirect because it's not an actual measurement of how much the cow ate. It's based on related information, such as the cost of extra feed needed to make extra milk, and then larger cows have greater maintenance cost. So that's factored in as well. And it gets about 8% of the weight in TPI. So, okay, it's not as much emphasis as it would get in net merit, but I would argue that we're kind of in the same neighborhood. So what that means to me is, in some broad sense, we have agreement that this is an important enough trait, even with the greater uncertainty associated with it, that we would want to make a trade-off and put some selection emphasis on increased efficiency rather than in certain other areas, because the value of that increased efficiency to you is so large. And Tom has talked about in the past that better net merit, higher net merit in your herd means that you can profitably produce milk at a lower milk price. And so this is actually related to that. Greater efficiency means you're able to weather tough changes in the milk pricing system. Now, there are a few ideas floating around. Do we want to publish residual feed intake? Sometimes that's a little hard to understand, maybe hard to get our heads around. So one idea is that we would publish a breeding value for feed saved. This is what our colleagues in Australia do, for example. So a positive number is desirable. So if the PTA for feed saved is plus 300, that means that cow consumed 300 pounds less feed during a lactation than she was expected to. And then in the same sense, a negative number is undesirable, because a cow that has a negative breeding value is eating more. In other words, she's not saving feed, she's requiring extra feed. So we could easily do that sort of calculation and put it on that basis if that's easier for folks to understand. But Rob Templeman from Michigan State gave a very nice presentation at the Dairy Science meeting that demonstrated the mathematical equivalence among a lot of these measures of RFI. So feed saved is a different way to express it, but it's not really a different trait once you take the math apart. So we'd get to the same place. And so in the feed saved, what you really have is in the top left, you see there's variation in how the residual feed intake of animals. Then you add in a piece that's the variation based on maintenance, right? So at the same level of production, a smaller cow is more efficient than a larger cow. And then we add all that variation together and get feed saved. This was some work done by Chen Yao and Kent's group. So what are we doing now? There was a recent announcement that some of you may have seen. So the Council on Dairy Cattle Breeding and the Foundation for Food and Agriculture Research, are going to fund the ongoing collection of new data. So it's a slightly different group of participants. It's a subset of the earlier group. So it continues to be the folks who took the lead at Michigan State, Iowa State, University of Florida. So we like working with those folks. Madison, and then AGIL. Some of you might be saying, why isn't dairy forage on there? And I believe that's because they're about to do a major renovation and reconstruction on their facilities, so this isn't the best time for them to be participating. And this will allow us to collect somewhere on the order of 500-600 phenotypes a year ongoing. And then about the last thing I have is my postdoc, Bing-Ji Lee, has done some work to find, I'm not going to really dig into what all this means. I just want to show you that we've identified some regions in the genome that are associated with better feed efficiency. Why is that interesting? It's not interesting because I expect any of you to care about pathways involved in carbohydrate metabolism. If we find SNPs that have a large association with feed intake, we can put them on when the next time they revise the genotyping chips, we can put those markers on. And that will give us a little bit of a gain in reliability from having those associated markers. We've demonstrated this with fertility SNPs we added after work with Pete Hansen's group and some others. So it's a well-proven strategy. We have some questions we're interested in. How is feed efficiency related to methane production? Because we at least need to have an answer to that, to talk to consumers and advocacy groups. Are there ways to manipulate the population of microorganisms that live in the rumen to improve feed efficiency? That's still maybe some pie in the sky work, but we're interested in it. And are there correlated traits that we can use to get more reliable predictions of residual feed intake? So for example, somatic cell score has a high correlation with clinical mastitis. We don't have very much clinical mastitis data. We have lots of somatic cell score data. So we can use the somatic cell score observations to improve the reliabilities of the clinical mastitis predictions. And we may be able to do the same thing with the RFI. So we had a pretty successful grant, lots of institutions involved. We got several thousand genotypes. It lets us produce breeding values that we can rank animals on. There's enough genetic variation that we think we can make progress by selecting for it. Okay, and if it's put into net merit at the economic weights Paul worked up last year, it would get about 16% of the weight, so a little bit more than in TPI, but not, say, radically. It's not getting 50% of the weight. And we have funding now for the next few years that will support the ongoing collection of data so that we can keep working to improve these evaluations. I have to put some acknowledgments in. I not noted here, but I would like to clearly note the cooperation and participation of Mike Vandehar's group at Michigan State, colleagues at University of Wisconsin and Iowa State, University of Florida. This has been a nationwide effort that's involved lots and lots of people to get us to this point. It's certainly not the product of only Agile work or the people at Agile. I don't want to take the credit that other people have earned. And when we get to the panel, I'm happy to answer any questions you all might have.